Okay, hello everyone. So I'm going to talk about metabolomics data processing and statistical analysis. So most of the concepts are already been mentioned in previous lectures today and yesterday. So I'm just basically repeat and also with some illustrations also within the context of metaboanalyst. Since tomorrow you're probably going to practice, so this one going to hope to prepare you guys better. And also there's some most things should be familiar. So some is special questions and or things you need to pay attention. So here is that although metabolomics is kind of recently new, but basic concepts of analyzing metabolomics data is the same, which is all the omics, especially functional omics like gene expression, proteomics, metabolomics, or lipidomics, all the things is share the same concept. So if you understand this big concept, it will help you understanding how to use the tools, how to put it in different categories to things. So this is a big framework. So the raw data processing is always most difficult part, and because it's machine specific, sequencing, microarray, mass spec, NMR, every machine spit out the data is very different format, and it contains the signals, noises that's very different and need a specific, a lot of time is proprietary tools, to pass out the data and get the data that's ready to be analyzed. And usually analyze means statistical computing, and which usually require a data matrix to work on. But before, this is really time consuming. So I'm not going to talk more on this because all the previous ones covered, but this one really needs a lot of your attentions, and from study design to data quality check to outlier removal and to everything. And finally, it's ready for the statistical analysis. So statistical analysis is just several concepts. So one is comparison. You want to use your ANOVA t-test or more advanced things to see whether some features are statistically different. These features deserve your attention, and they think this is more related to a disease or certain biological process. And the second one is you need to find the patterns. And this kind of patterns is could be just the data speak for itself. You just cluster data close to each other, or data point close to each other means that they are more working on the same biological themes or concepts or processes. You want to find out these patterns and the things, find out more about it. And the other one is classification. This is more advanced, like machine learning or predictions. So this is this one data speak for itself. This one really you want to build a model to capture the more advanced characteristics, which won't be obvious here. But this is more for complex data on predictions and diagnosis. This is more advanced, but it's a very important thing. And finally, is that you find these patterns and features you want to interpret it. So my previous lectures, including several other lectures about how to do this enrichment analysis or pathways, network analysis, and ontology analysis, and the integration. So it's all kind of how pipelines, how do you do it. But today, at least this lecture is on this process and how do you have a feeling about your data, mainly from statistical. So for metabolomics, currently you do targeted and untargeted, and the untargeted basically is the binning or picking, and you found these features. You don't usually directly analyze a raw data point, which is going to be super big, and the majority is sparse matrix, don't contain any good signals. You need to do this first to get the important features, and here you just actually need to identify the compounds. You build a data matrix, and now you do this exploratory data analysis or functional analysis. From this data matrix, you actually do you can do from here do the over-representation analysis, or directly from here just like a quantitative enrichment analysis or Mummy-Chalk approach. Directly you can get a function. So all this route actually is doable, and this is ready to use tools to do it. So today I'm going to talk about some main features within Metabolomics about allow you to do some data processing and normalization, and some output from PC and PLSDA. How do you interpret that? And advanced analysis, I just briefly mentioned about the biomarker analysis. It seems quite popular modules. A lot of people are using it. And I removed some slides from here because today there's so much talk on PC, PSD. I hope you guys already get a very good understanding. So data processing is that, this is from NMR, is that you need to do this identification and quantification. And from then we analyze this compound concentrations. And all you can do is binging on pickings and find these things. And for the MS, and this, I missed the first day. I don't know your favorite tools to do a picking or alignment. And here is something I found it quite popular, useful, is XCMS and MZMatch, which is already built within this XCMS Online. And you can do this clean up your untargeted metabolomics data, make sure the final pick is more like the real and much reduced, and just a few thousand. So you get these picks and you need to align them. So it's, when you compare across the different samples, you know they really, hopefully they are actually talking about the generated from the same compound. So you don't want to. And finally, you're talking about a data. So this data is we call it clean data, and it takes a lot of effort to get to this stage, but it's all worth it once you get here. And we can use a lot of tools. You use Excel, use Metabolomics, or use SPSS or anything. It's ready to accept this data. So usually for Metabolomics, the first row is your sample names, and second is you can label which class it belongs, and which time point or things, and if your metabolite concentration, or could be your peaks with intensity. So this is at this moment, and ready for analysis. So if you use peaks, you put in the other transposed, because its peaks can be several hundred or several thousand, and usually you put it in another way. But still, usually you need to supply or insert one extra column about this phenotype, so that when you analyze, and the program will understand which group it belongs to, so it can be colored or classified. And so this is kind of metadata. Sometimes you need to manually add it. So data normalization and filtering, data filtering and normalization, I think it's been covered quite a lot before. So data filtering is basically we need to try to reduce the number of features, because the more features we have, the less power we are going to have, because the multiple testing corrections and so some directly affect your final p-value or something. And for in omics data analysis, most widely used, actually default, if you probably didn't realize this, the majority of the genes or majority of metabolites starting to change. And under this assumption, we build all these statistical models to do the test. So if you really found this majority of things changes, so actually you compare apple versus the orange, because this the cells or the things is in a different state. It's become incomparable if majority things change. So assumption is that the majority consistent, although they fluctuate or vary, it's not statistically significant. Only a few minority will change. So based on this assumption, developing all these statistical models for the gene expression for metabolomics, so it's all the same. And so if we're filtering these features based on their variations, it's supposed to be safe. So you don't need to afraid you lose some real signals. So if they're really almost constant and doesn't change, you just filter them out. It should be a good thing to do, and definitely improve your later data analysis. After doing the filtering and you're going to do some normalization, it's because especially for metabolomics, it changes. So variation is a lot. And if you visualize to the PCA or heat map on the raw data, you can see the huge difference. And a lot of this difference is a batch effect or some other things that's not supposed to be related to your experimental conditions. So this one can be addressed by different normalization methods using your like internal standard, which to address your machine-specific, platform-specific, or round-to-round specific batch effect. But sometimes you also want your data to be normalized as like a normal distribution. So concentration usually is follow a log normal. So if you usually the default, you should do a log transformation on your data, because after that, the data is more or less comparable and looks more like normal. So this is a kind of similar. Gene is also follow the same thing. When you transfer the log, it's much more looks uniformly. So there's a transformation. There's also a data scaling. It's called basically Z-score auto scaling. Or you can normalize by the sum or the mean or median. And this time is especially for certain samples. It's have a large volume, a large mass, or something is consistent all up or all down. The whole sample change. So you can adjust that. So this kind of things you can usually find it from visualization and back. Okay, we can try to adjust that. And sometimes you can normalize by certain reference compounds. If you really think about certain compounds supposed to be constant, you can always against that. For the urine, people do it like a creatinine normalization, and you can also do a normalization by a reference sample, which they call it probability quotient normalization. And you choose a pooled sample or reference healthy sample. You can try to normalize against that one. So you can a lot of things statistically you can just define it and do it. And this is a lot of things that really depend on your data. It's not just you have to do this, have to do that. So how do you choose the best one? Is usually you need to visualize your data somehow, and so commonly that is used for is PCA and heat map, and box whisk plot also used for in certain time. But when we have lots of features, it's just impossible to visualize all of them altogether. So this is a box plot, and sometimes if you get all your samples, just not the features, all your samples are plotted together, you can clearly see overall shift, batch effect is fine. And here's one example. I use non-normalized raw data almost. So you can see certain sample just standing out, so not together with them. So in this case, it's more or less justified because it's so clear difference for this sample. And also if you see it's something on the PCA, you can almost guarantee you can find it in the in the heat map, because these two this is a high level, this is low level. Almost you can see each cell basically across different sample, across in the feature, you can see exactly what this feature expression or concentration in each data point. You can see them actually. So you can see this one, this feature standing out. You can see this feature actually all these things. So give you another levels of comfort. See something changes on the PCA, you can actually see why it's changed, because it seems all the concentration is so high, it seems unjustified. So you can, in this case, such as you can choose sum normalization or normalized by divided by their own total sum or median as well, should adjust this. So dealing with outliers, and really you need to be careful. It's just unless in extreme cases you can do it, but a lot of times people just cherry picking and choose the one that seems more different, and so that you remove the sample that overlap between two categories, and that's usually not recommended. So you really need to have the biological justification. Statistical justification is usually hard unless it's really standing out, something's totally wrong. And but also there's some method. It's a non-parametric test, or like also random forest, which is more robust. It's some quantitative difference, not that okay. You can adjust them. So up to you upload the data and visualize and filtering and normalize and see looks good. You can do some statistical analysis, t-test, ANOVA. If you're doing this, is basically the first pass and see whether there's something there, because it's very simple. You can do it and see whether there's some feature. You make some intuitive sense, and then you can do PCA, PLSD. What I suggest, do simple ones before you really jump to the more advanced ones. So there's a quite difference between PCA or PLSD, because PCA is like a clustering. It shows all the data, the clustering by itself. Basically, a sample similar to each other, supposed to be more close to each other on the PCA score plot. And also like hierarchical clustering will do the same thing. It really doesn't consider your class labels. But PLSDA or the other like random forest or the vector machines, they try to find the features or try to do the separations and related to the class label. So this is very different. So if your data actually on the PCA looks quite different, and this different separation is related to already to your phenotypes, then you're pretty sure you get a much better result here. So if it's so that's a big difference. So if you want to do a good separation here, and usually if PCA and the clustering doesn't show a good pattern, and you want to use supervised method, which is a very natural next step, but keep in mind that supervised method always have the intention to please you. Basically, try to create some patterns that make you feel, oh, this is what you want. I can try to generate patterns. So you need to really pay attention to the issue called overfit. So you need to do cross-validation, something to guard against these things. And that means your data need to be larger, okay? If you here, you need probably 3 samples or 4 samples each group, 5, and here probably need 10 or 12 samples in order to have a relatively good cross-validation result. So especially, so you have a large biological effect, so you can use a small sample. But once you expect your population is more heterogeneous, have the biological effect not that strong, so you need to have more samples. So that's very natural thing to do. So keep in mind, PCA assuming that they capture the main variance of your data. So they're assuming your main directional variance is main data characteristics. So this is something you keep in mind. Sometimes the PCA, the first variance is actually a batch effect. So that's probably not what you want. So if your data, your biological effect actually the main variation, then that's perfect. PCA will give you best result, just very satisfying. So the PCA usually working with just 2 plots, scoring plot and loading plot. So score plot shows all your samples, and loading shows you the features, so all your peaks and compounds. So if you see the separations on the scores, you're looking, so here's the samples, and here are the features that drive this sample towards this separation. So you want to see these features positive associated with this group, and this sample and this feature. So this feature is positive associated with this one. Basically, this one is more abundant in this group. So PCA have a very good visual interpretation, so it can help you to understand, and it's very amenable for a lot of data understanding at a high level, and quickly pick up something that can help you interpret the patterns. So PLSD is, as I mentioned, it's a supervised, and by supervised is to try to maximize in the covariance between your data and class labels. Compared to other method, like supervised method. PLC actually is almost the worst in terms of overfitting. It's always produce the separation patterns, disregarding whether there's a real difference or not. So PLC are really people doing in the field, they actually suggest against using PLC because it's so easy to overfit, and even you can simulate two group populations, actually there's no difference, but PLC will give you a separation. So that's the thing that it's really you need to do a double check whether it's true, and use PLC or probably use more other approach like a random forest or support vector machine, see whether there's separation there. And usually this method is working more robust and bad performance in a lot of ways. The good thing why we use PLC instead of use as support vector machine or random forest is PLC give you visual appealing result, and they give you a separation things. And SVM and the random forest all most likely is a black box, and you know it works, but how it works you don't know, and it's just all hidden, so it's not clear. So this is a PCA versus PLC. You can see almost guaranteed better separation, always improve. So if you have a PCA slight separation, PLC are very good. So within Metabolomics, the PLC is based on the regression. So regression is you can think about it, it's naive. Basically, regression is using your concentration against the continuous response variables. But if we're doing a classification, we have to class label, which is categorical, it's not continuous. We have to, from this label, from case and control or ABC towards a number, and do regression on it. So you can see ABC will be 1, 2, 3, low, medium, large will be 2, 3, 1, because you know this is low, but computer just think it is alphabetical order. H starting with H is 1, starting with L is 2 and 3. So it will be choose just convert to a number, whatever they think is the same. If you really have your group have certain degrees of severity or something, you can choose it group 1, group 2, group 3, and make sure it will convert to 1 to 3 and follow order. Using this one, it will convert this order won't be following this thing. And then they use this regression against these numbers from your concentrations, and it generates separate data patterns. So this is quite common. But the thing that if you really you change your class labels, like this, it will 1, 2, 3, 1, 3, 2. It will generate slightly different patterns because a group associated with one particular label have this label is converted to different number, we're going to slightly different. So this is regression because it's in quantitative. But if you're doing classification, it won't change. Whatever your class label, the overall accuracy will be the same. But if you see the visual pattern, it will change, okay? If some people can say, I changed the class label and seeing the pattern is different. So my advice is don't change it, just keep it consistent because of that built-in regression thing. So performance measure in PLC is quite more several layers to help against the overfit. So then you guys are familiar with R-square, Q-square. This is cross-validation things. And the prediction accuracy, basically cross-validation, see how good you can predict the things that hold out. And also permutation test. I'm going to just give you some that. So cross-validation, I'm not sure you guys are familiar. So basically given a limited number of samples, and we don't have the luxury of have an independent cohort to validate. We just use our own data, and we can try to do the validation. For example, we have 13 samples, and we just divide into 10, 10, 10, and we build a model in the 20, and use this model predict the class label of another 10. So this is chaining data set and the test data set. So it's 20 samples and 10 samples, and you move the other one and use this 20 samples as chaining and predict this 10, and you use this one. So you just basically rotate 3 times and predict and see how good you are, how good this model is. So the assumption is that you should more or less have a balanced sample. In each chaining, you have probably 10 control 10 disease, and they say 5, but you need to really predict more or less close. But sometimes people have a very small data set. If you really spread into further cut into 3 and use two-thirds to build a model, you probably don't have enough data to train the model. So people in this time use leave one out cross-validation, leave one out basically just one as the test, and all the things used for building model. This time just guarantee the model enough samples for the model. So if you have a small data set, this is probably the only thing you can do to generate a good model, relatively good model to do it. Oh, I didn't, let me see. So the prediction is basically you predict how many times you predict is correct, and you the proportion is 97%. So basically predict 100 times, and 97 is right, and three times is wrong. And the other prediction is another testing is called a permutation test. And the goal is not to see how good is model, but what to see is whether your model is significantly different from null model. So this is basically asking whether you get a real signal. There's something real difference between the two samples. And in order to do this, we need to create a null model. The null model is created by randomly shuffling the Y labels. So a control and a case will be randomly shuffled, and recalculate this this value, either it's prediction or R square or Q square or separations, and from this shuffled data. And then we can calculate the p-value. This p-value is not based on model, it's based on permutation. So it's more practical, empirical p-values. And so I think the result is basically look like this. So this, if we shuffle the label and recalculate this statistics, and if it's a null model, we should see most, let's say, normal distribution is just here. But your original label, the separations or statistics should be far away, and this means there's some real difference. And this model captures the real difference, and so this is safe. If you are your original label, the statistics based on your original label is here, and you're in trouble. You're not sure whether it is real difference or just it's no different from random shuffling. So basically that says you cannot see anything about this model, because even randomly you can get the same thing, right? And sometimes now, because we can get a p-values as any significant. If you're doing 1 million times, we can get this p-value just 1 or 2 out of 1 million. But most time I see if we just have 1,000 permutation, and the most time we can see is p-value less than 0.001, because if we continue permutation, probably 1,001 another time we'll get something is better. So we don't know. So this is p-value like this. But this is how you're going to interpret empirical p-values. So biomarker analysis, I'm going to be, this is slightly different from the other analysis. Okay, this is a continuation of that test. When you do the classification, and here's two commonly used called accuracy, is that, for example, out of this 22 samples, you getting okay, all the prediction, you get this 9 out of 13 is correct. This is your accuracy, and the error rate is 1 minus accuracy. This is your error rate. It's very common. But this kind of performance measures has troubles in a lot of clinical settings. It's because our population, if we don't choose intentionally control it, and we'll get very unbalanced. And for example, every 5 cases in 1,000 people have a cancer incident. So if we just take the whole survey and we don't control it, if we predict, we're going to use that population, we can predict everybody is fine. We get 99.5% accurate. And so such model is not that useful, because it's because the population is quite unbalanced. So in clinical, if we want to do some screening test, and diagnose of things, we need to use different measures, not accuracy, use sensitivity and specificity. So sensitivity here is at a true positive rate and specificity true negative rate, and you can see it here. I assume you guys are very familiar. If a prediction and positive and actually is positive is true positive, and predict negative and actually is negative is true negative. So these are two things we combined, and in terms of accuracy. But when we clinically, we separate these two, sensitivity, specificity, and two measures to guard against this imbalanced sampling things. So clinical don't use accuracy, so they use sensitivity and specificity. But these are two values. How can you combine these two? And so this is a kind of common things. I'm just put it here. So these two populations. This is control. This is disease. And you see there's overlap, right? You have to choose your threshold to diagnose this negative, this is positive. Once you choose that threshold, then we can see this is true negative. And here is this blue on top of this red. This is a false negative because it's actually the disease, but it's below this threshold, so it's false negative. And if you see here, this is definitely true positive, but this red underline is blue. It is a false positive because it's actually not. So we actually, when we do the real diagnosis, we have all these things, and we can get this sensitivity, specificity in a real life example. And because it's two values, and two values not good for selecting, for ranking things, we always want to combine them together. And how we combine sensitivity and specificity. And one popular approach is called the ROC curve. It's the receiver operating characteristics, which is developed during World War II, and then found out a lot of nice features with these things, and they used in almost widely in clinical settings. So they combine the true positive versus false positive for the binary classifier as a cutoff variate. So it's if you see my previous, if you see it's actually very easy to generate. So this is two original populations, and you have your cutoff. You just don't know. You just the two populations, your measurement. You just cut off 1, 2, 3. You just get all the cutoff. At each cutoff, you calculate false positive, false negative, all these values, and you can get this dots here, and then you connect these dots, and you actually get this ROC curve. So it's even the ROC curve seems the name is foreign, at least to me, but when how you generate actually it's very easy. You're just going through this cutoff and get these values, and it naturally combines the sensitivity and specificity. And here there's a very high specificity, so but the sensitivity is not high. But if you go here, sensitivity is almost 100%, but you use a lot of false positive because the specificity here is reduced here. But here it's if you go here, it's balanced. It's just okay, good specificity, and sensitivity is also high. So it's basically give you a balance of sensitivity specificity, and how they actually summarize in this thing, this area under the curve. So the area on this curve as the performance. So biomarker analysis is a very popular module in metabolomics. It has this classical univariate ROC curve. Basically, for all the concentration values you measured, it just move. You sort it from low to high, and cut off at each point, and draw a ROC curve. See whether that compounds actually have certain diagnostic values. But the more powerful ones, unless you're lucky, you just found my biomarker actually really different between. But a lot of time you combine multiple biomarkers. You can use these popular tools like SVM, random forest, or even PLCA, and create biomarker modules. I think, okay, I missed ones, a lot of logistic regression. You can actually use all these things that combine as different compounds and build a model to predict. And again, I emphasize that once you do these kind of things, you need to have a relatively large sample. So I suggested 20, 12 probably fine, but when it's very less, you really get the ROC curve is not that confident. So this is the output. You're doing this single biomarker. You get this compound. You can click and see how good that they can this value. If you find this value, how if you have this overlap between two groups, and you can see if you have a cutoff here, and there's some false positive, false negative here, but you can actually see from here. And it is not quite clear if you use multiple biomarkers, because it's multiple biomarkers. Some could be high, some be low, but this is one you can manually pick several biomarkers and build models and see how good they are. Okay, I'm done. Any questions?